Every complex oscillation is merely a sum of simple periodic sine waves. By isolating individual frequencies, we transform a chaotic time series into an ordered spectrum of magnitudes and phases. Think of the signal as a path traced by a vector rotating in the complex plane. The transform measures how much the signal correlates with a specific frequency by winding the data around a circle. When the winding frequency matches a signal component, the center of mass of the circular plot shifts away from the origin. This displacement creates a peak in the frequency spectrum.
Mathematically, we multiply the function by a complex exponential and integrate over time. This process projects the signal onto a basis of orthogonal complex sinusoids. Orthogonality ensures that each frequency component is independent. Integrating the product of two different pure frequencies over a full period always results in zero, preventing cross-channel interference. Digital systems process finite sets of samples rather than continuous functions. The discrete transform uses a summation to map a vector of n samples to n frequency coefficients. A standard discrete transform requires n-squared complex multiplications. For large datasets, like high-definition video, this quadratic growth creates a significant computational bottleneck for real-time optimization.
The fast Fourier transform optimizes this by recursively breaking a transform of size n into two smaller transforms of size n divided by 2. This divide and conquer strategy is the Cooley-Tukey algorithm. At the core of the fast algorithm is the butterfly operation. It combines the outputs of smaller transforms using complex weights called twiddle factors, minimizing redundant arithmetic. Optimization reduces the complexity from n squared to n log n. For a signal with 1 million points, this transition reduces the required operations from 1 trillion to just 20 million.
Information is never lost during the transform. It is simply redistributed. A narrow pulse in the time domain spreads across all frequencies, while a pure tone occupies a single spectral point. The transform yields complex numbers. The magnitude tells us the strength of a frequency, while the phase describes the relative timing or shift of the wave within the signal. To perfectly reconstruct a signal, we must sample at a rate at least twice the highest frequency component. Sampling below this Nyquist limit introduces permanent errors, known as aliasing. Aliasing causes high-frequency energy to fold back into lower-frequency bins. In optimization, this is a constraint that must be managed with low-pass anti-aliasing filters.
Optimization tasks often involve noise reduction. By transforming to the frequency domain, we can zero out coefficients representing high-frequency noise before transforming back to the time domain. Applying the transform to finite segments causes spectral leakage at the edges. Windowing functions like the Hamming or Blackman window taper the signal to zero at the boundaries to minimize this. For signals that change over time, like speech, we use the short-time Fourier transform. This creates a spectrogram showing how frequency content evolves across a sliding temporal window. There is a fundamental trade-off in resolution. A narrow window gives precise timing but blurry frequency data, while a wide window gives sharp frequencies but vague timing. Data compression utilizes the fact that most natural signals are sparse in the frequency domain. By storing only the most significant coefficients, we minimize storage while maximizing fidelity. Two-dimensional transforms are the backbone of image compression. The discrete cosine transform, a relative of the Fourier transform, isolates spatial frequencies to remove redundant visual details. Magnetic resonance imaging scanners collect data in K-space, which is the spatial frequency domain. The final image is produced by applying an inverse Fourier transform to this raw data. In engineering, we use the transform to analyze system responses. Mapping differential equations to the frequency domain simplifies convolution operations into basic multiplication, allowing for rapid stability optimization. Engineers minimize mechanical wear by identifying resonant frequencies. The transform reveals which frequencies cause the most stress, enabling the design of targeted damping constraints in structures.
Additive synthesis builds complex timbres by summing harmonic sine waves. By optimizing the amplitude envelopes of individual partials, we can recreate the sound of any musical instrument. Compressed sensing is a modern optimization technique that reconstructs signals from fewer samples than the Nyquist rate. It assumes the signal is sparse in some domain, usually frequency. To recover a signal from undersampled data, we solve an L1 norm minimization problem. This finds the simplest frequency representation that is consistent with the few measurements we have collected.
Radar systems use the Doppler shift, a frequency change, to calculate object velocity. The Fourier transform extracts this shift from reflected pulses to optimize collision avoidance in autonomous vehicles. Radio telescopes scan the cosmos for periodic signals. Fast Fourier transforms allow astronomers to sift through terabytes of noise to find the faint, rhythmic ticking of distant pulsars. Quantum computers use a specialized version of the transform to find the period of functions exponentially faster than classical bits. This is the key component of Shor's factoring algorithm. Modern AI models use positional encodings based on sine and cosine functions. This allows transformers to understand the relative positions of words in a sequence by utilizing spectral properties. Physics problems like heat diffusion are solved by transforming spatial data into the frequency domain. Complex differential equations become simple algebraic ones, which are much easier to minimize and solve. Electrical grids must maintain a constant frequency. The Fourier transform monitors harmonic distortion in real time, allowing grid operators to minimize energy loss and prevent equipment damage. Geologists use the transform to map underground oil and gas deposits. By analyzing the frequency reflections of sound waves through different rock layers, they optimize where to drill. One of the most powerful features of the transform is the convolution theorem. It states that convolution in the time domain is equivalent to pointwise multiplication in the frequency domain. This theorem allows us to apply complex filters to high-resolution data extremely fast. By using two fast Fourier transforms and one multiplication, we bypass the heavy cost of time domain sliding. Data transmission uses frequency division multiplexing to send multiple streams of data over one cable. Orthogonal frequencies minimize crosstalk, ensuring high throughput with minimal error rates. Traditional Fourier analysis assumes signals are stationary. For transient events, like an explosion or a bird chirp, the standard transform fails to capture when specific frequencies occur. The wavelet transform solves this by using functions that are localized in both time and frequency. This allows for multi-resolution analysis, optimizing the capture of both sharp spikes and slow drifts. Adaptive filters use the Fourier transform to adjust their parameters in real time. They minimize the error between a desired signal and a measured one by tracking frequency changes dynamically. Switching to a spectral perspective is more than a mathematical trick. It is a fundamental optimization tool that reveals the hidden structural patterns governing the physical world and our digital data.